So let's look at this question of non-independence that spatial autocorrelation causes. We'll look at the question of non-independence non-spatially for this example. So let's look at the effects of a non-random sample on the mean and variance of that sample that is used to estimate the mean and variance, or the true mean and variability of the population. So we'll create a population, artificial population of numbers here. I'll just call it true pop. True population, I'll say that's equal to our norm, and that'll have 1,000 values in it that range with a mean of 0 and standard deviation of 100. So this creates a normal distribution. So if I just run that, for example, and I look at true population, you see it's a bunch of numbers. And these numbers have a standard deviation of 100 and a mean of 0. But they're generated randomly from the normal distribution within that, using those parameters. So let's look at the histogram of these. Hist of true population. You can see here it looks like a normal distribution. So we'll consider this as our true population. So this set of numbers, and the mean of this set of numbers, I just say mean of this set of numbers is mean of true population. And it happens to be 4.7965. And again, this is our population, that's the mean. So let's take a sample from that population. So I'll start by taking a sample of 40, let's say. So to take a sample, I'll just call it S1 equals sample. So that's a built-in R function to sample any numeric vector like population. And I say, okay, what do I want to sample? True population. And how many samples do I want? 40. And I'll just run that. And I can look at the mean of that sample, or even the histogram as well. I can say hist S1, looks like that. Doesn't look quite normal or anything, but it's a random sample, so it's an independent random sample of that population. And I can take the mean, and it's 21.41. That's quite far from the mean of the actual population, which is 4.79. And that's normal for a sample. Samples can vary quite significantly from the true population mean. The larger the sample size, the closer it will be to the true population mean. So if I was to take a random sample instead of 40, let's say I took 400, and I run that and I look at the mean, it's getting smaller towards 4. If I take a bigger sample, like 800, of course, that's almost getting up to the size of the population. When I take the mean of that, 4.36, it's already down around the 4.79 mark. And of course, if I took the entire population, that's just the mean of the entire population. But that defeats the purpose of statistics, of course. Statistics are to estimate that mean through sampling in some way. So how could I do better with just samples of 40? Well, I could take many samples of 40. So I could say, let's replicate. So replicate, let's say 100 times, sampling, the sampling that's going on there, of 40 numbers at once, which is an independent random sample. But all I'm interested here is in the mean of these. So I'll say the mean of those samples. And I'll bring this down a little bit so it's all on one screen. So like so. So replicate will take any statement such as the mean of 40 numbers independently random sampled from the true population and replicate it however many times you say here, like 100. So in the end here, I will have a set of 100 averages based on that sample size. And according to what's called the central limit theorem in statistics, the average of these 100 averages should be closer to the population mean, which is, we know, 4.79, than any given single sample would be. This is what's called the law of averages. You may have heard that. Not many people understand what it means. So if I run this now, and I look at S1, it contains a whole bunch of means, and if I look at the average of those, the mean of X, no, not X, but S1, sorry, it's 3.97. And so that's fairly close to 4.79, much closer than a single sample of 40 is. So I took 100 single samples of 40 independent random observations from the true population. Each time, I computed a mean and stored it to get 100 means, where each mean represents the average of 40 random selections from the population. And the mean of those means is quite close to the population. And it will also be normally distributed. That's another property of the central limit theorem. So if I say here, hist of S1, it will look normal, approximately. You see that approximate normal distribution shape to this subsample, or number of samples. The more times I do that, the closer to the population mean it will get. So let's just say here, each time I compute that, I want to say what is the difference. So I'll say here, mean of S1, and then I'll subtract that from the true mean, mean of true population. So mean of true population, put that on a separate line, minus the mean from 40 random samples, the average of 40 random samples taken 100 times. So I can just look at that here, for example, run these two. It gives me, there's a difference of 2.57 in this case. If I run it again, that'll be different, 3.21. And there's one 4.43, so it's very close. 1.96 difference, 3.36 difference, 0.58 difference. That's a slightly larger deviation of 2.82 difference from the true mean. And I could just say the absolute value so they're not negatives. I'll just say ABS, like so. Then I'll run them again, 0.9258. So they're all pretty close. Sometimes, once in a while, they're off a bit, and that's normal for what you would expect. We're taking 100. If I take, let's say, 1,000, I'll have smaller numbers, and I won't get these big 3.5. So now I'm taking 1,000 means of 40 random samples from the true population. So that first one was quite small. So notice how small they tend to be now. I'm not getting any of those 3s or 4s or anything. And the more samples I take, let's say I take 10,000, some of them will be almost identical to the true population mean. But mostly here hovering around 0.1 something, sometimes 0.2, but nothing like 1 or 2 like that. And that's because we're taking independent random samples, which is fine. So we're getting a good estimate of the mean. So I'll take that back down to 1,000 replications. Now, what if we were lazy samplers? And instead of sampling each time 40 from the true population, let's say for whatever reason it's very hard to get the samples from the true population. So those 40 samples are very costly. Even and it doesn't matter how many times we do the 40 samples, each is fairly costly. So we decide instead to take smaller samples. But since we need a sample size of 40, we're just going to take a smaller sample from the true population and repeat those numbers instead. So I'll just go down here and I'll say, okay, I'll call this one S2, and that'll be equal to, again, replicate. And then I'm replicate 1,000 samples. But this time, I'm going to say I want the mean again, just like before, so the mean of something. And this will be the mean of repeating rep sample, open parentheses, true population. I'm just going to bring these down here to different levels. So true population. And I'm just going to take 10. So this again is sampling 10 independent random samples from the true population. But I want, because 10 is less costly overall, and I need 40, I still have to then, whatever 10 I get here, I have to repeat each of those 4 times. So that's the rep part here, and I'll put 4, like so. So rep here simply repeats this single sample 4 times. So if I just look at that part by itself, for example, and I was to do this just here, what I'll see is that after the first 10 numbers, so there's the 10th number, I have repeating 78 again, 78, minus 104, minus 104, 19, 19. So you see here that the 10 original numbers that were randomly sampled from the population are just repeated 4 times in total. Two, 3, and 4. So that's a lazy way of sampling, isn't it? Because we're repeating the same set of observations a number of times. And that means that our 40 here, so the fact that we have 40 samples, it's not a true 40 independent random samples, is it? So let's just run that. And then let's look at the mean of S2. So the mean of S2 is 5, whereas the mean of S1 was 4.64. And what we want to look at then is the absolute difference between the true population mean now and the mean of S1 and S2. So we have that absolute value there. And I'll just do the same here for this one. So it'll be the mean of S2, the mean of means. So we'll see those two values printed out. So in the first set, we're 0.34 away from the true mean. The second set happens to be, in this case, 0.25. 0.14 and 0.5. 0.3 and 1.05. So what you'll notice here is that the first number, maybe I'll just print them right beside each other down here. The first number represents, I'll say here, print. Or no, we don't need to print it, it's already being printed, that's fine. The first number represents our true random sample, and the second one, the non-independent random sample. So we'll just run those and we can see them there. So 0.14 versus 0.96, 0.7 versus 2.86. Once in a while, by chance, we still get a smaller one for the non-independent random sample, so a smaller difference from the true mean. But in general, almost all of the time, the replicated set of samples will have a larger deviation from the true mean of the population, as you can see here. Once in a while, it'll be smaller, but most of the time, larger. And that'll be even more obvious if I take less samples, like 100, instead of 1,000 for each one of those. So generally, that second one with the duplicated set of samples will always be larger. So if I was to look at, let's say, the histogram of both of these. So here we're just looking at the mean, but there's also a thing called the variability. And I'm going to go back to 1,000 just for this illustration here. So 1,000 fake samples and 1,000 real samples. And I'll plot out the histogram. First I'll say hist, and I'll plot the second one first, which is the 10 random samples repeated 4 times, and then 1,000 of those means. So I'll say hist, and I'm going to give S2 and breaks. I'll give equals 20 breaks on the histogram just to give it some resolution. And again, it'll be normally distributed approximately. And I'll put y lim equals C. So this is the y limit. So we can have up to 1,000 in each one. So I'll put that up to 1,000 there. See how that looks? And that's a bit too much. Maybe you put it up to 400 like that. And that's still probably. So I'm just trying to get the right y scale here. 250 maybe, like so. Oh, that's not 250. That's 25,000. There we go. Okay, so I have that one. Now I'll plot the second one, or the first one I should say, which is the true 40 random samples repeated 1,000 times. So that's S1 breaks 20, y lim 0, and I don't want any color in here, so I'm going to say col equals null and border equals red. Oh, well, I forgot one thing. I have to put the add, and then after that, add equals true for adding it to the current plot to see it. There we go. I'm just going to bring that up a bit. There. So what we can see here is we have overlain the 2 histograms. So the red histogram here represents these values here. So that's 40 independent random samples taken from the true population with a computed mean. And that mean is of those 40 random samples is repeated 1,000 times, and that's the red. Then the gray bars that you see here, they represent the random sample of 10 taken from the total population or the true population. That random sample then being repeated 4 times to get the same sample size, 40, as in the first case. So we know that's not a true random sample of 40, even though there's 40 numbers. It's only really a random sample of 10. And then that's repeated 1,000 times. Again, so we have 1,000 averages of those. We just call them the fake random samples. And what we see here are the spread is very different. So the variability or variance around the mean, which is around 0, remember it's like, I think it's like 4.7 or something. So around the mean of around 4.7 here, we see that the gray is much more spread out. And that means it has a higher variability than the red. Even though both had 40 numbers in the samples, because one was replicated, its effective number of random samples was 10. Whereas the bars here, the red ones, are from true 40 random samples in the means. And so it has less variance, it's tighter around the mean. So independent random samples affect both the mean and the variance of a set of samples from a population. And remember, most of the time, well, almost all the time, we don't know the true population. We only have the samples in which to figure it out. And that's why sampling is so important. And that's why independence of samples is fundamentally important to represent the true, or to estimate the true population mean and variability, for example.